Hi everybody, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, and I'm on section 6.2, which is on finite groups. I'm talking about group theory now, which is a topic I just started a few days ago. But group theory is a very big topic, and there's a lot of different examples of groups, some very important groups, and so now I'm starting a new subsection. This is subsection 6.2.1, which is on symmetry groups, which is a very important category of groups. And today I'm going to talk about probably the simplest type of symmetry, which is mirror symmetry, also known as bilateral symmetry. So anyway, let's begin. So, yeah, like I said, I'm starting a new subsection. I might as well introduce this one first, symmetry groups. So group theory is really about symmetry. I mean, sometimes it doesn't seem like it's about symmetry because there's a lot of abstract groups that a lot of people study, both mathematicians and scientists. A big application of group theory is studying symmetries of various objects. And as we'll see, there's a lot of different types of symmetries. There's probably a lot of types you never even considered before. But anyway, that's kind of an overview of where we're going. And in particular, today I'm going to talk about mirror symmetry, which is also known as bilateral symmetry. And I think we're all familiar with this type of symmetry because we all use mirrors. Most people use mirrors every morning when they go to the bathroom and take a shower and brush your teeth. Probably use mirrors a few times a day, and I know we use them when we drive. Obviously, we have to see where the traffic is in back of us. So, we're very used to mirrors these days, and I think it's pretty obvious what mirrors do. I mean, mirrors create an image of the object that you're looking at, but the interesting thing about the mirror image is that it has a symmetric relationship with the object that it's reflecting. You can think of the mirror image as being in back of the mirror, and it's symmetrically placed with respect to the plane of the mirror, meaning that for every point on you, there's a point on the mirror image that's on the opposite side of the mirror, the same distance away. That's another way to say it. And when we say that an object has mirror symmetry, what we're really saying is if we placed a mirror about a particular axis, a particular plane in the figure. If you're talking about 3D figures, the mirror, you have a mirror plane, a reflection plane, and most animals have very close to mirror symmetry or bilateral. It's usually called bilateral symmetry, and there's a lot of evolutionary reasons for this. I'm not going to go into that, but turns out that our mates find us more attractive the more symmetry we have. Also, there's practical reasons for being symmetric or nearly symmetric. So humans are a case in point. And there's a picture of a naked man on the bottom. I wouldn't say it's a porno picture because you can't really see his thing. Got a line going through it anyway. And the point of this picture is this man. If you put this is a 2D picture, so if you put the vertical line through the center of the man, it basically looked like his left side looks like a mirror image of his right side. I mean, not exactly. This is supposed to be a typical man, but it's a very good approximation. We all have bilateral symmetries. Our left sides look basically like our right sides, and I guess that's part of what makes us attractive. So I think you get the idea. Anyway, that's what mirror symmetry is. And what does this have to do with group theory? Before I even show the next slide, so a group, the way you're supposed to think of a group, remember, is a special type of set, but it's a set with a binary operator, which we usually call group multiplication. And this is a very simple group. There's a group with only two elements. It's called the mirror symmetry group in this case. of the man. And one element, and the way you're supposed to think of group operation, you're supposed to think of elements of a group when they apply to symmetry of an object. You're supposed to think of those as transforming the object. So they're kind of a list. There's kind of a set of transformations that you can do on a particular object. In this case, this man. So what can you do to this man? Well, you can leave him alone. I mean, remember, every group has an identity element, which we usually write as E. Well, E, if you're thinking of the group elements as transitions of your objects, then the E, the identity element, always leaves your object alone. So E does nothing. It leaves the man alone. So, but then there's another element of our group, which I call little r in my book. This is the element that does the mirror symmetry operation. It acts like a mirror. So if you reflected this guy about this horizontal plane going through the middle of his body, what would happen is his left and right sides would get switched. I mean, he basically looked the same because, like I said, he already has bilateral symmetry, or at least approximate bilateral symmetry. He's not going to look exactly the same. I mean, most of us have our heart on the left side of our body, so his heart will now be on the right side. So his heart will have moved to the other side of his body, and I guess some of the other internal organs will as well. And maybe his right side didn't look exactly like his left side. Maybe, I don't know, maybe the right side of his chin was a little smaller than the left side of his chin. Now it's going to be the other way around. So you basically switch the left side to the right side. If you were the man and you had this done to you, you'd be pretty freaked out because you would see everything being reversed. If there was a sign on your wall, it would be backwards. And I think I actually did watch a movie once. I think it was called Journey to the Far Side of the Sun. It was a pretty bad sci-fi movie, but I guess turns out there was another copy of the Earth on the other side of the sun, and it turned out he accidentally went to the other side, and he ended up in a world that everything was reversed. He was seeing mirror images of everything, which really freaked him out. I mean, not a bad premise, but not a very good movie. Take my word for it. But anyway, so that's mirror symmetry. And, now I'm just going more of the formalities of this group. And like I said, this is a very simple group. It's a group with just two elements, E and R. E leaves the man alone, or E, you can apply it to anything. It doesn't even have to have symmetry. You can apply it to a baseball mitt. Baseball mitts are not symmetrical. But if you applied this R operation to a baseball mitt, maybe the baseball mitt started out for a left hand, because most baseball players use the mitt on their left hand. If they're right-handed, they have to catch in their left hand. But maybe you have a left-handed baseball player, and once you reflect the baseball mitt, it becomes a right-handed baseball mitt, which looks different from the left-handed baseball mitt. But that's what the mirror symmetry operation would do to a baseball mitt, because a baseball mitt does not have mirror symmetry. It doesn't have bilateral symmetry. Not everything does. And so those are the two operations of the group. Why is it a group? Well, you can check that it satisfies the four axioms. It has identity, obviously, the element that doesn't do anything. And the identity is always its own inverse. And this element R, it's pretty easy to see that it's its own inverse too, because if you apply R twice, think about the baseball mitt. If you applied the mirror symmetry operation twice to a baseball mitt, first you start out where it's fit for your left hand, then you apply R, now it's fit for the right hand. You do it twice, it's fit for the left hand again. So it's pretty easy to see that applying the mirror symmetry operation twice gives you the identity. So R is its own inverse, but every element has an inverse. E and R are both their own inverse. And the only other thing to check is associativity. Well, closure is obviously closed, because you apply E times E is E, times R is R times E is R, and R times R is E. So you can see it's closed. And what about associativity? I don't think I'm even going to bother going through that. You can do the work. Associativity is always the hardest one to check. But it is associative. Just take my word for it. And you can even I didn't do this in this chapter, maybe I should have, but you can make a Cayley table of the mere symmetry group. It's a 2x2 table where E's are on the main diagonal, so it looks like ER. The first row is ER, and the second row is RE. Pretty uninteresting group. And the other thing I want to say about the mere symmetry group, it is a cyclic group of order 2. It turns out that up to isomorphism, there's only one group of order 2, and that's the cyclic group of order 2. And since the mere symmetry group is a group of order 2, it has to be isomorphic to C2, the cyclic group of order 2. Anyway, so I think that's enough said about the mere symmetry group. Anyway, that completes my video for today, and thank you for watching. Long live math, and I'll see you guys next time. Bye.